Okay, hi everyone. My name is Connor Bush. This is my submission for homework 2, part A. I'm going to read part A and then get into it on my iPad right here. So part A, given 3 streams with temperatures of 80, 65, and 90 degrees Celsius, containing species A at concentrations Ca of 0, 1, and 0.5, flowing at 0.5, 0.3, and 0.6 meters cubed per second, respectively, into a perfectly mixed tank with a cross-sectional area of 1 square meter and a drain hole of 0.1 square meters. Calculate the liquid height, temperature, and concentration of A if the mixing tank has been operating under these conditions for a very long time. So to get started, we are going to want to derive 3 differential equations for the change in height, temperature, and concentration of A with respect to time. And then we can go into Python and use a root solver. So once it reaches the steady state that we have a solution for all 3. So getting into it, I have a schematic drawn here. We have 3 streams coming in, and each 3 streams has all 3 of these parameters or initial conditions. And then we see that the whole has a cross-section area of 0.1 square meters, and then the cross-sectional area of the tank AC is constant at 1 square meters. So to get started, we're going to look at how we derive the equation for dH dt, change in height with respect to time. We know that volume is equal to the product of height and some area. So if we look first at the change in volume with respect to time, that is equal to the flow rate coming in subtracted by the flow rate going out. So if we substitute H for volume, we get that the cross-sectional area of the tank multiplied by this difference in height, because the height is changing, but the cross-sectional area of the tank is not. We can keep that out of the differential. We get this expression here. We know our flows coming in. So since we have 3 streams, we're going to have to do a summation from 1 to 3 of these flows. The great thing about this is that we can change this number however we want to accommodate for however many streams that we will have. We need an expression for Q out. We know that Q out, or just the flow rate in general, has units of meters cubed per second. We can get that by multiplying a velocity by area, in this case area of the hole. And then from energy balance, we can say at the top, the gravitational potential energy equals the kinetic energy at the bottom. We can set the height to 0 at the bottom. So we have this expression here. Gravitational potential energy equals, sorry, that is incorrect. The kinetic energy at the bottom, mass cancels, and if we solve for velocity, we get this expression there for velocity. So our expression for Q out becomes the cross-sectional area of the hole, leaving multiplied by the velocity, or 2gh. And then since we are looking at this expression right here, if we solve for h, this will help get our initial guess for when we need to use that in the root solver. So these 2 expressions are very helpful in the intermediate steps of this process. So if we solve for dHdt by moving algebraically, I can't write. Moving over the cross-sectional area of the tank, we get this expression here for dHdt. So next, if we use mass balance, similar here, and we need an expression for concentration, if we simply just multiply our differential for velocity, or volume with respect to time by concentration, since that's changing, that turns into an expression like this. Very similar to what we have above. We're going to leave CA and not CA out because CA out is equal to whatever leaving concentration. Since we reach steady state, all of the liquid streaming out is the same concentration. If we break this up in terms of height, which we know, it turns out to be something like this. And then we're going to need to use the product rule to separate that out. So that comes out to be this expression. And then if we just move over this CA/dH/dt term and then divide by H, we are left with an expression for dCA/dt. I'm going to copy all of this over for the sake of time. Subtract CA/dH/dt and divide all of that by H. So now this is our expression for dCA and dt. So finally, if we use a similar approach for dt/dt, and try to multiply this temperature by the volume, we're going to need to also multiply by density and the heat capacity. Heat capacity has units of joules per unit mass per unit temperature, we'll just say Kelvin. If we multiply Cp times density times temperature, we're left with this set of units here. So similarly to our changing concentration with respect to time, if we multiply all of our flow rates in and flow rates out by this rho Cp term, you see that they cancel. As they are also constants. And then if we separate out dH from the volume, left again with this expression of the cross-sectional area of the tank multiplied by dH/dt. And then temperature stays within the differential because it is changing. And then if we do the product rule and then move everything over to isolate the change in temperature with respect to time, we are left with an expression similar to dCA/dt. All of this divided by height. And this is our expression for the change in temperature with respect to time. So we have all three of these differential equations here, and we can go into Python and code these. So I'm going to stop sharing my iPad screen. And then I'm going to share my computer screen, and then we're going to get right into it. So we need to import a few libraries as tools. So we are into or importing NumPy and then a few tools from SciPy. And then here we need to, or next we need to initialize our initial conditions. So in an array, we're going to have our flow rates of 0.5, 0.3, and 0.6. This is all in cubic meters per second. Our concentrations coming in are going to be an array of 0, 1, and 0.5. These are all in moles per cubic meters, and then Tn not an array. Then we have 80 degrees, 65 degrees, and 90 degrees, all in units of degrees Celsius. And then also we know that the cross-sectional area of the tank, AC, is equal to 1 cubic or square meter. Cross-sectional area of the hole is equal to 0.1, correct, square meter. And then our gravitational constant, G, is 9.81 meters per second squared. So we have all of these parameters listed. We can define our function. RHS for right-hand side, we're going to need some time, eventually vector with all of our initial conditions, and then all of these final conditions. This V here is a vector, so we're going to unpack that as T, or height, H, Ca, concentration of A, and then T, temperature, unpacking that, and then our expression for Q out we derived to be the cross-sectional area of the hole multiplied by the square root of 2 times G times H, or velocity leaving. So now we can do our 3 differential equations, dH dt. That's going to equal the sum of all of the Q ins subtracted by the Q outs divided by the cross-sectional area of the tank. That one was pretty simple and straightforward. dCA dt, that's a little more complicated. So that's going to be the sum of the product of the flow rates coming in multiplied by the concentrations coming in. So it's subtracted from the flow rates going out by Ca, the concentration leaving the tank at steady state, so it's all equal. This is all divided by cross-sectional area of the tank, and then we subtract this whole thing from the product of concentration of A by dHdt, and then all of this is finally divided by height. And then I'm going to copy this part as it is very similar for what we had for temperature, as I explained earlier. So everywhere that there is reference to concentration, we just change that out for temperature. And then now we just need to return an array of all of these 3 differentials. So we can use that in the root solver. So now we're going to store our solution into this variable, which is called sol for solution. We're going to call the root function. We're going to need to use this lambda function in reference to V because of the immunity factor. So we're going to call within this lambda function our right-hand side. For T, we're going to set that to 0 for steady state. Here we're able to leave V as V because we're using this lambda function. We're going to use our values for Q and not Ca the TA in not the initial parameters for concentration, and then T in not. And then we're going to need initial guesses. So like I was saying earlier, we needed that expression for height as the initial guess. So we need to make another array for our initial guesses. So this is going to be sum of all of the initial fluids coming in divided by the cross-sectional area of the whole. And then this is going to be squared divided by 2 times G. Let me make sure my parentheses line up here. Great. And then initial guess for concentration, we're just going to call that 0.5, and then 70 degrees for the temperature, sorry. Make sure that looks good. We're going to unpack our solution here into this V naught sort of variable. And then if we call that, we can see what our steady state conditions are. So here, first, we have the height. So around roughly under 10 meters of liquid level in the tank at steady state, a concentration of around 0.43 moles per cubic meter of A in the tank, and then around 81 degrees Celsius for the steady state condition. So that is part A, and then in the next video, we will go over homework 2, part B. Thank you.